preparing for a Propulsion Engineer interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you compare rocket engine cycle options for a new launch vehicle? Engine cycle choice is a balance between performance, complexity, reliability, and cost. I would compare gas generator, staged combustion, expander, and pressure-fed cycles using chamber pressure, specific impulse, thrust level, restart needs, and development risk. Pressure-fed is simple but tank-heavy. Gas generator is proven and easier to cool. Staged combustion gives high efficiency but is demanding. Expander works well for smaller cryogenic engines. The mission usually decides the right cycle. While answering, focus on why cycle choice matters. Compare pressure-fed, gas generator, staged combustion, and expander cycles, and connect each option to thrust level, efficiency, reliability, cooling, cost, and mission requirements. Question 2. What do specific impulse, C*, and thrust coefficient tell you about engine performance? Specific impulse measures propellant efficiency, thrust per unit weight flow. I treat it as a mission-level metric, not the only design target. Characteristic velocity, C*, reflects combustion performance independent of nozzle expansion. Thrust coefficient captures how well chamber pressure becomes thrust through the nozzle. If measured ISP is low, I separate losses: injector mixing, incomplete combustion, heat loss, nozzle divergence, or off-design expansion. That breakdown points to the subsystem needing work. Make sure to cover ISP, C*, thrust coefficient, effective exhaust velocity, how test data is interpreted, and why separating combustion, nozzle, and system losses matters during performance troubleshooting. Question 3. How do you choose nozzle expansion ratio for sea level versus vacuum operation? Nozzle expansion turns thermal energy into directed kinetic energy. I size area ratio around the expected ambient pressure profile and mission phase. Underexpanded flow wastes potential thrust. Overexpanded flow can separate, causing side loads and instability. A sea-level booster needs conservative expansion, while an upper stage engine benefits from a large bell or extendable nozzle. I also consider contour efficiency, cooling, manufacturability, and separation margin during throttling. In your answer, talk about expansion ratio, ambient pressure, underexpanded versus overexpanded flow, separation risk, altitude compensation, nozzle contour efficiency, and how sea level and vacuum engines require different design choices. Question 4. What factors drive injector design in a liquid rocket engine? An injector must meter propellants, atomize them, mix them, and avoid instability. I look at pressure drop, element type, spray pattern, momentum ratio, face cooling, and compatibility with the chamber acoustics. Higher pressure drop improves stability and distribution, but costs pump power. For liquids, I also check cavitation margin and start transients. A good injector is not just efficient, it produces repeatable combustion across throttling and mixture ratio conditions. Be sure to mention injector pressure drop, atomization, mixing quality, element selection, cavitation margin, face cooling, acoustic coupling, and why injector design strongly affects combustion efficiency and stability. Question 5. How would you approach cooling design for a high-temperature thrust chamber? Thermal management starts with the heat flux map. I estimate gas side heat transfer, coolant properties, wall temperature limits, pressure drop, and material margin. Regenerative cooling is preferred when the propellant can absorb heat without coking or boiling problems. Film or ablative cooling can protect hot zones, but may reduce performance or life. I validate the design with coupled thermal structural analysis and hot fire data, not just steady-state calculations. While answering, focus on regenerative, film, and ablative cooling, heat flux prediction, coolant pressure drop, material temperature limits, coking risk, thermal stress, and how hot fire data validates thermal models. Question 6. How do you diagnose and mitigate combustion instability? Combustion instability is pressure oscillation coupled with heat release, and it can destroy hardware quickly. I first identify the mode: chugging, buzz, or high-frequency acoustic instability. Data from dynamic pressure sensors, high-speed imaging, and frequency analysis is critical. Mitigations include injector pressure drop changes, baffles, acoustic cavities, mixture ratio adjustments, or startup sequencing changes. I would never treat it as random noise. It is a system-coupled problem. Make sure to cover low and high-frequency instability, coupling between acoustics and heat release, diagnostic sensors, frequency analysis, and mitigation methods such as baffles, cavities, injector changes, and sequencing. Question 7. What are the biggest design challenges in rocket turbopumps? Turbopumps are difficult because they combine high speed, cryogenic fluids, tight clearances, rotor dynamics, and cavitation risk. I focus on required head rise, flow rate, NPSH margin, inducer design, bearing loads, seals, turbine power, and transient operation. Efficiency matters, but reliability and stability matter more. A small inlet pressure error can trigger cavitation, reduce head, and damage blades. Good design needs analysis, testing, and conservative margins early. In your answer, talk about pump head, mass flow, cavitation, NPSH, inducer design, rotor dynamics, seals, bearings, turbine power, cryogenic constraints, and why turbopumps are reliability-critical components. Question 8. How would you select propellants for a launch vehicle or spacecraft propulsion system? Propellant selection is mission architecture, not chemistry alone. I compared density, specific impulse, storability, toxicity, ignition behavior, temperature requirements, cost, and ground operations. LOX RP1 gives high thrust density and simpler tanks. LOX LH2 gives excellent ISP but large, complex cryogenic systems. Hypergolics are reliable and restartable but toxic. For spacecraft, long-duration storage may outweigh peak performance. For launch vehicles, thrust-to-weight and operations often dominate the trade space. Be sure to mention performance, density, storability, toxicity, ignition behavior, cryogenic handling, ground operations, cost, and trade-offs between LOX RP1, LOX LH2, methane, and hypergolic propellant systems. Question 9. What makes ignition and restart reliability difficult in rocket engines? Reliable ignition is about delivering the right propellant state, ratio, energy, and timing every time. I would design a start sequence with purge, chill down if needed, valve timing, igniter verification, and controlled ramp rates. For restartable engines, residual heat, trapped propellant, tank pressure, and ullage conditions become critical. I like using instrumentation-based commit criteria because a safe abort is better than forcing ignition into an uncertain chamber. While answering, focus on start transients, purge and chill down, valve timing, igniter energy, propellant conditioning, ullage behavior, restart constraints, abort criteria, and how sequence design prevents hard starts. Question 10. How would you plan a hot fire test for a new propulsion component or engine? A good hot fire plan proves requirements while protecting hardware and people. I define test objectives, operating points, red lines, instrumentation, calibration, sequencing, and abort logic before firing. Key measurements include thrust, chamber pressure, feed pressures, temperatures, flow rates, vibration, and dynamic pressure. I also plan post-test inspections and data reconciliation. The best tests are boring because the hazards, assumptions, and decision points were handled before ignition. Make sure to cover test objectives, instrumentation, calibration, red lines, abort logic, safety reviews, measured parameters, data reconciliation, and how hot fire tests verify models and expose integration issues. Question 11. How does mixture ratio affect propulsion system performance and hardware design? Mixture ratio affects performance, temperature, cooling margin, and component sizing. I would start near the optimum for specific impulse, then adjust for hardware constraints. Fuel-rich operation can reduce gas temperature and protect turbines or chamber walls. Oxidizer-rich operation may improve density impulse, but creates material compatibility challenges. The selected ratio also changes pump power, injector pressure drops, and residual propellant at shutdown. In your answer, talk about stoichiometric versus optimal mixture ratio, effects on ISP, flame temperature, cooling margin, turbomachinery, material compatibility, residual propellant, and system-level optimization. Question 12. Walk me through a first-order thrust chamber performance calculation. At a first pass, thrust is mass flow times effective exhaust velocity, or chamber pressure times throat area times thrust coefficient. I estimate C star from propellant chemistry, choose chamber pressure and expansion ratio, then apply efficiency losses. From thrust and ISP, I back calculate total mass flow and split it by mixture ratio. This gives initial throat size, injector flow requirements, tank sizing inputs, and a baseline for detailed analysis. Be sure to mention thrust equation forms: mass flow, chamber pressure, throat area, C star, thrust coefficient, nozzle efficiency, mixture ratio, and how first-order sizing feeds detailed design. Question 13. How do you build a pressure budget for a propulsion feed system? Feed system pressure budgeting prevents surprises during test. I start at required chamber pressure, add injector pressure drop, line losses, valve losses, cooling channel drop, acceleration effects, and margin. For pressure-fed systems, that drives tank pressure and mass. For pump-fed systems, it drives pump head and turbine power. I also check transient cases because water hammer, chill down, and regulator dynamics can violate a steady-state budget during operation quickly. While answering, focus on pressure budgeting from tank or pump outlet to chamber, injector drops, line losses, valves, cooling channels, regulators, transient effects, margins, and impact on mass. Question 14. A hot fire test shows low thrust and higher than expected chamber temperature. How would you investigate? When test data shows low thrust and high chamber temperature, I avoid guessing. I compare measured chamber pressure, mass flow, mixture ratio, C star efficiency, nozzle conditions, and sensor health. A lean shift, injector blockage, flow meter error, or cooling flow reduction could explain it. I would verify calibrations, inspect hardware, review valve timing, and reconcile the data against the model. Root cause comes from evidence, not the loudest hypothesis. Make sure to cover structured troubleshooting, sensor validation, comparison against analytical predictions, possible causes like lean shift or blockage, hardware inspection, timeline review, and evidence-based root cause analysis. Question 15. When would you choose liquid, solid, or hybrid propulsion for a mission? Liquids, solids, and hybrids solve different operational problems. Liquids offer throttling, shutdown, restart, and high performance, but need complex feed systems. Solids are simple, dense, and launch-ready, but hard to throttle or stop once ignited. Hybrids improve safety and throttle ability, yet often struggle with regression rate and combustion efficiency. I would choose based on mission controllability, storage, cost, safety, required impulse profile, and risk. In your answer, talk about controllability, throttling, restart, storage, complexity, safety, regression rate, cost, impulse profile, and when liquid, solid, or hybrid propulsion is the best fit. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.